Welcome again, boys and girls. We are continuing with our study of chemical changes, and we are touching on the hot questions which always give us trouble during examinations, and we are taking this revision class to address those sections or aspects which give us a lot of problems. So if you look at this, we did rates of reactions, and we talked about the concentration and factors that are affecting rates of reactions, so we now want to move on to measuring rates of reactions. And then we will look at the mechanism of reaction and catalysis, and then chemical equilibrium and factors that is affecting equilibrium, and then the equilibrium constant and the application of equilibrium principles. So we are moving into something quite interesting. If we look at this, we are going to go into the fine details of chemical equilibrium, apart from the introduction we had earlier on. So here we are going to make sure that we know what equilibrium is, the expressions for equilibrium constant Kc, and calculating Kc using equilibrium concentrations, and calculating equilibrium concentrations using initial concentration and Kc value, something which was introduced in grade 11, which you are supposed to be practicing and applying more rigorously. And then also look at the relationship between Kc and Kp, and then factors that affect equilibrium, and lastly the Leach-Taylor's principle. Okay, so you'll see that equilibrium is a measure of how reactants and products are being formed. So if you remember in our introduction, we agree when we were measuring the speed at which a reaction is taking place, we say that we always start with reactants. So when reactants are participating in a chemical reaction, they get used up. But where do they go? They form products. Okay? They form products. So here we can use R for reactants and P for products. So you'll see that as this reaction proceeds, there are reaction dynamics that kicks in terms of the concentrations as they vary, while the concentration of reactants is decreasing and the concentration of products is increasing. There is a tendency of the reactions becoming reversible. Why do they become so reversible? Because they will be trying to counter or to balance up concentrations of products and reactants. So if more reactants are being produced and such that more products are being produced so that the reactants are getting depleted, the products tend to decompose or break down to form reactants again, such that the reaction itself is no longer a one-way process where reactants are only forming products, but products themselves will reach a stage where they start breaking down, and then as they break down, they form reactants, the initial reactants we had in the first place. So when this happens, we say we are in a state of a reversible reaction. And in a reversible reaction, we are saying in as much as reactants combine to form products, products also break down to form reactants. And a point in time is reached when the rate of the forward reaction is equal to the rate of the reverse reaction. So if I'm to represent it here, using symbols. So I'm going to say this is a forward, F for forward reaction, rate of the forward reaction, while R is the rate of the reverse reaction. So we noted earlier on where we agreed that when we are making representations of the rate of the reaction, how do things happen? So like in this case, we can say, if you look at this picture, you can see that these kids playing here, they are not in equilibrium. If you compare it to that representation there, so we can say that maybe this is a product, while this is a reactant. So the product is few. So since it is few, so we can say here it is lighter. So that's why it is up. While the concentration of the reactant is still high, so it goes down there. So what do they need to do for this seesaw to be leveled up? So you'll see that maybe the reactants have to convert into products and reach a state of equilibrium. So when this seesaw is leveled up, we will say it will be in a state of equilibrium. So if you look at this, you can see that this is not equilibrium at all, because the quantities or the concentrations of either reactants or products is completely different from the concentration of the other. So the direction of reaction is not balanced, where we are expecting both products and reactants to interact interchangeably in opposite directions. Okay. So in nature, equilibrium does take place, where if you have visited tourist sites and see where we've got stalagmites and stalactites, these are representations of chemical equilibrium in nature. You can go and read more about it. So what are we talking about when we are talking about chemical equilibrium? Take, for example, the following reaction, where calcium carbonate, a solid, reacts with carbon dioxide dissolved in water, and then you see that this whole reaction takes place such that the calcium breaks down from the calcium carbonate to form calcium ions and form hydrogen carbonate. So you'll see that the reaction is represented in one way like that. But these very same products can also react in a reverse direction, such that calcium can react with hydrogen carbonate to form calcium carbonate, carbon dioxide given off, and water. Now, if you combine these two, you will see that reaction 2, this one, is a reverse of reaction 1. So we can measure how fast the forward reaction is taking place compared to the reverse reaction. So you will see that at equilibrium, the two opposing reactions occur at the same rate, meaning that at the same speed. So the speed at which reactants are combining to form products is the same as the speed in which products are breaking down to form reactants. So at that state, we say the reaction is in equilibrium. So you realize that the easiest way of keeping track of the reaction and how it is taking place is to monitor the changes in concentrations of the chemical species involved in the reaction system. So we are saying that concentrations of chemical species, they do not change once equilibrium is achieved or established, meaning that at that point in time when equilibrium has been established, the concentration of reactants is no longer changing, because whatever reactants that are going to form product, they are going to immediately break down back to form reactants. So we are having equal quantities of materials being exchanged between the reacting species, so their concentrations are going to remain constant. So if we are to make an a general representation of an equilibrium expression, we can consider the following system in which we have got W amount of A plus X amount of B. Need to give us, so these are reactants, they will give us Y amount of C and Z amount of D. So we are saying at equilibrium, Kc is equal to the concentration of C times the concentration of D over the concentration of A times the concentration of B. But before I proceed there, let me take you back to this representation here, where we are saying that in grade 11, you were taught how to represent what is called the rate law, where we are saying that the rate law, we say rate is equal to the reaction constant K times reactants. So let's say this is for the reaction going forward. So we can say Kf, F for the forward reaction. Okay. If we are to represent the rate for the products breaking down to form reactants, we are going to say rate is equal to the reverse reaction Kr, the concentration of products. So you will notice that if that's the case there, where we have got rate represented as for the forward reaction being equal to the rate constant K for the forward reaction times the reactants, while that one of the reverse reaction is represented as K reverse concentration of products. But we are saying that at equilibrium, the rate of the reverse reaction is equal to the rate of the for the forward reaction. So in other words, we are saying Kf of reactants is equal to, since we are saying the rate is the same at equilibrium. So if we are to play around with these quantities in mathematical terms, we collect like terms. So in this case, let's take constants on the same side and species on the other side. So what are we going to do? We are going to say if this is equal to that, so it means if I'm to bring Kr to this side, it's going to be Kf over Kr is equal to, if I take this to that side, it's going to be the concentration of products over the concentration of reactants. So when that happens, we are saying the expression Kf over Kr, it's a ratio which is measuring how fast the forward reaction is taking place with respect to the reverse reaction. But we are saying at equilibrium, this value is constant. It doesn't change. So meaning that we can say, since it is constant, we can combine these two species into Kc. C, meaning that it's a constant. This ratio is not going to change. It will give you the same value at any point of the reaction. Okay. So from now onwards, I want you to understand where Kc comes from. So Kc simply comes from a Kf over Kr, which comes from this representation, which starts like this, and then we are saying since rate is the same, it means that Kf reactants is equal to Kr products. And when we play with our mathematics like this, it gives us this representation. So from now onwards, boys and girls, I want you to understand that Kc is equal to Kf over Kr, which is equal to concentration of products over concentration of reactants. So even if you look in your textbooks or in your study materials, you will see that they will give you this as a general rule or a first rule which you are supposed to observe all the time you are handling equilibrium, that Kc is always equal to the concentration of products over reactants. So that's why we have got this representation we have here, where we are saying Kc is equal to, as you can see, these are products over reactants. And we now know where this whole thing is coming from. So we are saying that the numerical value of Kc is calculated using the concentrations of reactants and products that exist at equilibrium. Okay. So here we are. We are given an example where we are saying in the following expression you've got nitrogen reacting with hydrogen to give us ammonia. Please take note of the molar ratios or concentrations of these substances. So here you see that this is 1 mole of nitrogen reacting with 3 moles of hydrogen to give us 2 moles of ammonia. So Kc, take note of these superscripts. They are directly coming from the coefficients of our reacting species. So we are saying that Kc is equal to the NH3, the product, squared over reactants, which is nitrogen times hydrogen cubed, because we have got 3 of that here. Okay. If you look at another example where we've got a phosphorus pentachloride breaking down to give us phosphorus trichloride plus a chlorine molecule, the Kc expression, like we are saying, is always a product over reactant. So this is going to be PCl3 times Cl2 over PCl. L5. Okay. Here's another example again where we've got methane reacting with hydrogen. This is a mistake. It can't be like this. This should be oxygen here to give us carbon monoxide plus hydrogen. So this whole thing is misrepresented here. We can't have methane reacting with hydrogen and then we have oxygen from Norway. Okay. But anyway, you correct that one. Let's take a closer look at how we can carry out calculations involving equilibrium. Boys and girls, believe you me, this is every matriculant's nightmare. How you interpret the information you are given and how you make use of it. But I want to assure you that there is nothing so difficult about this. It is very important for you just to follow the step-by-step application of the interpretation of the data you have, given the background I've just illustrated now of how you relate materials as they are reacting, account for their changes in concentrations during the forward and the reverse reaction, bring them into an expression for equilibrium, that is Kc. Everything else will fall in place as you simply substitute quantities which you have. So you will see that we are going to learn how to handle information we are given and see how do we take it from the scenario we are given into the Kc expression. Okay. So like for example here we are told that 1 mole of hydrogen gas and 1 mole of iodine vapor are introduced into a 5-liter sealed flask, and the mixture is heated to a certain temperature, and the following reaction occurs until equilibrium is established. So if we take a closer look at this, we can see that this is a reversible reaction where hydrogen and iodine are reversibly reacting to form hydrogen iodide. So here's the question. They're saying at equilibrium, the mixture is found to contain 1.58 moles of hydrogen iodide. So what are the concentrations of hydrogen iodine and hydrogen iodide at equilibrium? And calculate the equilibrium constant Kc. So if we are to deal with this expression, you will see that it's quite interesting because the information is not so direct and straightforward. You have to be very vigilant and very careful with a very strong background of handling chemical quantities and be able to interpret them in chemical terms. So like for example here, what you should consider first before you do anything, you should consider that this is equilibrium. And in equilibrium, we only deal with quantities expressed in terms of concentrations. So whatever quantities you have, if they are not already expressed as concentration, your first port of call is to change them into a concentration. And how do you do that? You need to know your formulas of calculating concentration. So how do we calculate concentration from your grade 10 stoichiometry? We know that concentration C is equal to number of moles over volume. Do we have anything that speaks to that? Yes, we do. We've got 1 mole of hydrogen. We've got 1 mole of iodine. So let's deal with these quantities first before we go any further. So if we've got 1 mole of hydrogen, okay. Oh, let me say hydrogen like this. And then 1 mole of iodine. And then we've got 5 liters of a reaction vessel. So meaning that we can easily take these quantities, put them into this formula to give us concentrations. So like in this case, number of moles is 1 divided by volume, which is 5 liters. 1 divided by 5, you will see that it will give you 0.2 molar. So that's a concentration. For this one, it will also give you 0.2 molar concentration. If we read further, you will hear that at equilibrium, the mixture is found to contain 1.580 moles of HI. So we are saying equilibrium quantities, it's 1.58 moles of HI. So put this into this formula, put this quantity into this formula. You will see that if you say 1.58 divided by 5, how many moles of HI do we have? Let's do it by head. 5 into 5 is 1, 0, 3. Here is 1, 6. So this will give you 0.316 molar. So we've interpreted the quantities we know we have, or we know that so we can work out everything else we don't know from what we know. So what I'm emphasizing here is that the first port of call, you should know that as long as you are dealing with equilibrium, all your quantities should be in terms of concentration. So the intelligent approach here is to look carefully at your data you have, and if there is any need for you to change whatever quantities you have to a concentration, then do that as your first step, like what we have done here. And for you to be able to do that, you should know the general formula of calculating concentration, where we are saying concentration is equal to number of moles over volume. But the quantities you are given, if they are already in concentration, then there's no need to do any further conversion. You deal with them as they are. So, if you look here, our first question is asking, what are the concentrations of hydrogen, iodine, and hydrogen iodide at equilibrium? So, how do you deal with that? This is how we do it. So you use what we call the ICE table, where we are saying if you represent this expression, so for you to calculate the equilibrium constant for the reaction, you ought to account for the quantities you have as products and how they change when some of the materials react to form products. The reactants, how they change to products. So our initial concentrations is going to be the initial concentrations of hydrogen and iodine. So when you look here, we were given number of moles and we changed the number of moles to concentrations. So that's why you see we have got 0.2 there and 0.2 because we have changed the number of moles to concentration. So initially we have got 0 amount of hydrogen iodide. Okay. And what are the changes which are taking place? Okay. So you will notice that the changes here, they are changing by 0.158, 0.158. So if you change the concentrations there, you'll see that this is decreasing by 0.316. So you could be wondering, but we changed this 0.158 to a concentration of 0.316. What is happening? If you look at this reaction, if you consider the ratios, you will see that 1 mole of hydrogen and 1 mole of iodine gives us 2 moles of hydrogen iodide. So essentially their ratio is 1:1:2. So if that's the case, it means that if 1 mole of hydrogen reacts with 1 mole of iodine to give us 0.316 concentration of this, and we are saying their ratios is their ratio is 1:1:2. So how do we account for the concentration of iodine and hydrogen? So you just say the ratio of hydrogen to hydrogen iodide is 1:2. So if you say half of 0.316, what does it give you? Look at this. 2 into 2 is 1, into 3 it's 1, remainder 1, into 11 it's 5, remainder 1, into 16 it's 8. So it will look like we are repeating number of moles and presenting them as concentration. No, we are not. We are doing appropriate mathematical calculations. So this is now molar concentration, so don't get confused. This is now a molar concentration, not number of moles. So we are saying that if the initial concentration is 0.2 and it's changing by a minus 0.158, how much of the reactants are remaining unreacted? So this gives you 0.042 and this is 0.042, and the total amount of hydrogen iodide product which is formed is 0.316. So this is now the equilibrium concentration, and it is these equilibrium concentrations which you take to your equilibrium expression. So what is the equilibrium expression for this reaction? We know that Kc is equal to products over reactants, where our representation here will be such that hydrogen iodide squared over the concentration of hydrogen times the concentration of iodine. And these are their respective equilibrium quantities. So if we substitute them in here, so you'll see that this is for our products, 0.316 squared, because it's that. And here is the same as saying 0.042 times 0.042, which we can simply square like that. So you see that Kc for this reaction is equal to 57. If you take your calculator and you punch in these values carefully, you'll see that this will be 57. Okay. So here is yet another example which I want you to practice on your own, where we are saying 0.5 moles of hydrogen iodide is introduced into a 1 liter sealed flask and heated to a certain temperature, and under this condition hydrogen iodide decomposes to produce hydrogen and iodine until an equilibrium is established. And the analysis of the equilibrium mixture shows that 0.105 moles of the hydrogen iodide has decomposed. So calculate the equilibrium concentrations of hydrogen, iodine, hydrogen iodide, and the equilibrium constant Kc for this reaction. So you can actually see that this is just more or less the same as this reaction. But what is happening here is that this is now a reverse reaction. We are starting with the hydrogen iodide, and the hydrogen iodide is in 1 liter, and then after heating it, it breaks down it decomposes to form hydrogen and iodine. So in a similar manner, we just use the ICE table, and you represent things as they are like this. So when you do your interpretations in which you first convert these quantities, these are number of moles, and you've got the volume, you change them to concentration, and then you also change this number of moles to concentration, and then you plug it into your equilibrium expression, where you are saying Kc is equal to this. You see that it gives you 56.6. If you round it off, you will see that this is equal to 57, more or less the same as what we calculated here. The forward reaction is equal to the reverse reaction, or is 57 and so on. So we are saying that the expression and value of an equilibrium constant for a reaction, what do they mean to you? After calculating them, what is the expected interpretation you can attach to this whole thing? So we are saying that the expression for K depends on the equation, and the value of K or of the K applies to that equation only. It does not depend on how the reaction occurs. So the mechanism of the reaction is not necessarily important. So concentrations used to calculate the value of K are those measured at equilibrium, not the initial concentrations. Okay. So when earlier on when we talked about factors affecting rate of a reaction, you will see that some of them they don't necessarily apply here, because what is only important is the amount of materials that are existing at equilibrium, both as products and reactants. So you see that the relationship between chemical equations and the expressions of equilibrium constant is very, very important in telling us the direction in which the reaction is going to take place. And we are saying this phenomenon is used in industry to design chemical plants where materials are synthesized or they are reacted to target certain products by manipulating both their rate of reactions and also the equilibrium constant which is achieved or attained under a set of reaction conditions. So this is not just studied for fun. It has got a practical industrial application where you are expected to show an understanding of how all these things take place. So we are saying that the expression of equilibrium constant depends on the equilibrium equation written. So for example, for the following reaction, this one, the reverse reaction is expressed like this. So it's just like flipping over the Kc, meaning that you would expect that the reverse reaction is simply 1 over Kc because you are turning it upside down like that. Okay. So for that reason, you will see that we can similarly handle materials that are reacting in gaseous phase by applying the very same equilibrium constant expression. So the only difference here is that Kc, we used it to express the constants of the concentrations at equilibrium. But now, earlier on we indicated that some materials you can measure them, their concentrations in terms of the partial pressure if they occur as a gas. So like in this case, if your materials are in gaseous state, we are going, instead of having Kc, C for concentration, we are going to have Kp, where P is the partial pressure. So like for example, in this representation here, you can see that sulfur dioxide is a gas. It's reacting with oxygen, a gas, to produce sulfur trioxide, a gas. So their partial pressures are such that the partial pressure of the product squared over the partial pressure of the reactants, like this. And it gives you the equilibrium expression. You are expected to know how to make intelligent representations of the correct equilibrium expression by considering the nature of your materials, whether they are solids, liquids, or gases. So you also see that when it comes to solids, we are going to make a different interpretation because of how we account for the concentration of materials that exist as a solid in the chemical reaction representation. So here we are saying, considering the concentrations, we can express this reaction as Kc is equal to sulfur dioxide, SO, this is supposed to be SO3 over SO2 times O2, while an expression of the gas Kp is equal to the partial pressure of SO3 over the partial pressure of SO2 squared times the partial pressure of the oxygen. So if we assume that these are under ideal reaction conditions, so we will bring in the ideal gas law equation, which says PV is equal to nRT and P is equal to N over V RT, which gives you, of which we note N over V is number of moles over volume, which is concentration, molar concentration. So this changes to a concentration of concentration M times RT. So in a similar manner, you can actually see that if you express Kp and Kc, they are all related such that Kp is equal to Kc RT to the power of -1. Okay. We are not going to spend more time on that, but you will see that these relationships, they do help us to understand how heterogeneous systems work, of which at your stage we are not going to go much into that. But what I want you to master is how do you bring in together quantities which are not uniform. So like for example, we've got a heterogeneous equilibrium in which we've got calcium carbonate, a solid, reacting with calcium oxide, breaking down to give you calcium oxide, a solid, and carbon dioxide, a gas. If you look at this other one also, we are saying hydrogen fluoride, an aqueous solution, reacting with water, a pure liquid, to give you a hydronium ion and a fluoride ion. So you will notice that whenever we have got a species that exist as solids or pure liquids, we do not include them in our equilibrium expression. Why? Because we cannot account for their concentration changes. The concentration of a solid it doesn't change, it remains the same. The concentration of a pure liquid, it does not change. So you see that the expressions of equilibrium of these heterogeneous reactions is different. So like for example here, we are saying for this calcium carbonate, which breaks down a solid, which breaks down to a calcium oxide, a solid, plus carbon dioxide, a gas, you see that Kc is simply the concentration of carbon dioxide, because that's the only species you can account for its change in concentration. All these are the solid species you cannot. So in other words, we can say Kc can only, this whole expression, you can best represent it using Kp, which is equal to the partial pressure of carbon dioxide. If you look at this one, we are saying HF in aqueous solution plus water, a pure liquid. You are going to express it like this. So where you are supposed to say products over reactants, you will see that the only reactant you are going to include here is HF. You are going to ignore H2O because water is a pure liquid. Its concentration does not change. It's constant. So this becomes Ka. Why Ka? Because A, it simply states that acid dissociation. HF is an acid, and where you are supposed to express it as Kc, you can specify that this is a reaction involving an acid and express it as Ka. So ladies and boys and girls, you have got a lot more other examples which you can represent. But let me conclude using this one where we are saying where a solid substance dissolves in a liquid, you can also represent an equilibrium expression for the solubility of that substance, and we express what we call a solubility equilibrium. And instead of Kc, we write Ksp, where Sp simply refers to solubility product. It's the product of the ionic species that are produced as the material breaks down and dissolves in a liquid. So like in this instance, lead chloride breaks down to lead 2 plus ions in aqueous solution plus 2 chloride ions. So we are saying you do not incorporate a solid in an equilibrium expression because a solid's concentration does not change. So Kc for this expression is going to be the concentration of Pb2 plus times the concentration of Cl minus. And since this is solubility, something dissolving, Kc changes to Ksp, the solubility product, which is represented like this. When we meet next time, we will be answering questions where we will be implementing all these concepts which we have just described now. I hope this clarifies a lot of uncertainties surrounding equilibrium expressions, calculations, interpretations, and applications which we are expected to know as we prepare ourselves for end-of-year examinations. Thank you very much.